Good afternoon, and welcome to the research paper presentations presented by Major League Baseball. My name is Nick DeGansey, and I'm part of the Sloan Research Papers team. It's my pleasure to introduce Eric Martin, who will be presenting his paper, Predicting MLB Strikeout Rates. This presentation will last 20 minutes, with 5 minutes held for Q&A. If you are interested in asking a question, please raise your hand during the Q&A session, and we will provide you with a microphone. Now please join me in welcoming Eric Martin.
Thanks, Nick. Thanks, Nick. Appreciate it. How's everybody doing this afternoon? Happy Friday. I'm excited to see the great turnout, and I appreciate everybody coming to learn about my research. I recognize a few familiar faces in the crowd, so I appreciate you coming. A little background about me before I begin. As Nick said, my name's Eric Martin, and I'm currently a manager of partner strategy and analytics for the E15 group in Chicago. For those of you who don't know, E15 is an analytics company that does food, beverage, and hospitality support for many professional sports teams throughout all the different sports leagues. And I recently finished my master's thesis in predictive analytics from Northwestern University, and my focus was on sports analytics, and my research will, and the research we will discuss this afternoon was the subject of my master's thesis. Dan, if you could hit play on that. Thanks. On the right, we see a superimposed video of Yu Darvish throwing different pitch types. The difference in movement and velocity among his pitches are immediately apparent. More broadly, we know there's a strong relationship between the velocity of a pitcher's fastball and his strikeout rate. But what about the relationship between the different pitch types? We know that a pitcher's curveball is more effective if its movement is dramatically different than his fastball, and the effectiveness of these pitches is dependent on each other. It's the relationship among all of the pitches in a pitcher's arsenal, rather than just the characteristics of a single pitch, that are a larger determinant of success. There you go. The relationship among different pitches is sometimes referred to as a pitcher's stuff. Although a pitcher's stuff is one of the most often used terms to describe pitching ability, has no established definition. It can describe several combinations of pitch attributes, including velocity, movement, accuracy, location, sequencing, just to name a few. And so therefore, the interpretation of stuff can be decidedly subjective. Scouting effective pitchers based on this amorphous definition quickly dissolves into an abstract exercise, and that's where, that was really the genesis of my research. Oops, sorry if we go. There we go. My research addresses this problem by attempting to isolate the primary elements of a pitcher's stuff and model their impact on performance. And specifically, this research asks whether a model can effectively incorporate pitch speed, movement, and variability to predict MLB strikeout rates. Understanding the relationship among all pitch types thrown by pitchers may enable players and coaches to make changes to improve strikeout rates. So let's briefly take a look at other work that's been done in the field. Several analyses have examined how movement or velocity differences between consecutive pitches affect swinging strike or strikeout rates, and some of these pitch characteristics are listed here. However, all of these analyses examined pairs of pitches. None of the studies examined a pitcher's entire pitch arsenal or how several different velocities or movements among pitches have a compounding effect on each other. Other researchers have developed arsenal scores to quantify how a pitcher's pitch collection induces outs, and these methods add various rate statistics for each pitch type to create an aggregate arsenal score that can be used to predict pitching performance. But unlike the present analysis, unlike my analysis, however, these studies do not specifically examine the interactions among pitch types or explore how specific pitch characteristics such as velocity or movement affect the strikeout rates. More recent work has examined pitch tunnels and their impact on pitcher strikeout rates. As many of you know, pitch tunnels measure differences in pitch positions at the hitter's decision point, while considering release points, sequencing, break location, and velocity. And my analysis incorporates some aspects of pitch tunneling research by examining how differences in release points affect strikeout rates. And then finally, at least one researcher has used an entropy metric to quantify pitch deception and uncertainty by examining probabilities of potential outcomes. Pitch uncertainty was quantified based on the number of pitch types and the evenness or uniformity of a pitch distribution. And my analysis includes an entropy metric to quantify uncertainty resulting from the number of pitch types and their frequency. But overall, my research expands on this prior research, and it examines the interactions between velocity, movement, and frequency among all pitch types, and how these factors interact to affect a pitcher's strikeout rate. So I conducted this research last summer, and I therefore sourced PitchFX data from 2012 through the end of the 2017 season. I started with over 4.3 million pitches thrown by 1,500 different pitchers over those 6 seasons. And to ensure pitcher strikeout rates were representative of their pitch movements rather than from facing favorable matchups, short relief pitchers were excluded from my analysis. So I had to draw a line somewhere, and my analysis only included pitchers who both faced an average of 10 batters per appearance that season and pitched at least 1,000 pitches that year. The result was 402 remaining pitchers with over 2.5 million pitches that I analyzed in my models. The 2012 to 2016 seasons were used as the modeling and the training set, and 2017 was the test set. So my first step was to identify different types of pitches. And I found that PitchFX sometimes does not reliably label pitch types. For example, the top chart on the right shows Max Scherzer's pitches in 2016 as grouped by PitchFX. The PitchFX labels have significant overlap, as you can see, between comparable pitches, and several pitch types fall within multiple clusters. The overlap and inconsistency can be a problem if we rely solely on the PitchFX designations to identify different pitch types. But ultimately, however, the PitchFX designations are kind of irrelevant, right? I mean, a batter really only perceives the velocity and movement of the baseball. He doesn't care if it's a 2-seam fastball or a 4-seam fastball. So really, the label given to the pitch is not important. And as a result, I decided to employ a model-based clustering algorithm to identify different pitch types. And I used a method that was developed by statisticians at Carnegie Mellon University. And that research determined that model-based clustering provides the most accurate and reliable method of identifying MLB pitch types. So I used the methods outlined in that research to identify the clusters in my analysis. Specifically, for my research, each pitcher's pitches were assigned to several different cluster configurations based on velocity, vertical movement, and horizontal movement. I applied penalties based on to minimize the number of small clusters and to reduce high intra-cluster correlations among pitches. And the number of clusters with the lowest adjusted Bayesian information criteria values were used for each pitcher. And to eliminate outliers, clusters with fewer than 10 pitches were removed, as were pitches more than 2 standard deviations from their cluster means. The bottom plot on the right shows the result of clustering the same set of Max Scherzer pitches using a model-based clustering algorithm. It's a cleaner clustering of pitch types and removes outlier pitches that may have been incorrectly categorized. So how do we measure the difference between pitch clusters? Once each pitcher's pitches were assigned to clusters, I looked at a number of different ways to quantify differences between these pitch types. And one way to quantify differences is to measure the distance between pitch clusters. And there are several different ways to measure distances between pitch clusters. So if we used a traditional Euclidean distance, Euclidean distance fails to account for natural correlations between velocity and pitch movement. And as you can see on the chart on the right, as velocity increases, the amount of vertical movement decreases. So there's a natural correlation between those two variables. So as a result, I use the Mahalanobis distance to more accurately account for the correlations, the natural correlations between these variables. The pitch chart on the right shows the benefit of using the Mahalanobis distance to measure the differences between pitches. So let's take a look at that quickly, and I can exemplify the difference between using Euclidean and Mahalanobis distances real briefly. So relative to the 85 mile per hour orange pitch, below, a batter would expect the faster 90 mile per hour red pitch to have less vertical movement, obviously due to gravity and the speed at which the ball gets to the plate. But nevertheless, the Euclidean distance between the orange and red pitches is greater than that between the orange and the green. But the green pitch would be more difficult for a batter to pick up. It has almost the same speed as the orange pitch, but rises about 3 inches more. And the Mahalanobis distance accounts for this natural correlation between these variables, and it therefore provides a more representative measure of the difference or distance between pitches. And then finally, on the bottom left, the opposite arm angles for left and right-handed pitchers result in natural differences in the direction of movement, obviously. So the correlation matrices show that although the direction of movement changes, the magnitude of correlation among the variables remains fairly constant. And different correlation matrices were therefore used for left and right-handed pitchers when measuring distances between pitches. Apologies for the formatting error. There must have been something in the transfer, but I think everyone is able to get the information from that slide. Again, apologies for this. This might be a technical glitch, but that's okay. We'll work through it. So specifically, how does all of this come together? We talked about clustering. We talked about distance between clusters. And what variables did I model to predict pitcher strikeout rates? And I recognize that the plot on the right is a little bit of an eye chart. We'll walk through it quickly. But it demonstrates the different types of independent variables that I used in this analysis. My research needed to account for differences in the number of pitch types thrown by pitchers, because obviously some pitchers have 2 or 3 pitch types, and others have 6 or sometimes even more. So for the traditional pitch FX variables like velocity, horizontal movement, vertical movement, and pitch release points, 2 types of variance measures were used to measure differences among a pitcher's group of pitches. First, the minimum, maximum, and range for these variables were measured by comparing the centers of the different clusters, and you can see the lines that are coming out from the centers of those clusters on the plot on the right. So pitches outside the centers were ignored for these minimum, maximum, and range measurements. So for example, if you look at the velocity max label on the velocity axis, this pitcher's maximum velocity is the mean of his highest velocity pitch cluster. It's not the absolute maximum velocity pitch that he threw throughout the entire season. However, second, to account for variance among all pitches thrown, variables measuring the size of the interquartile range were also included. The middle 50% of all pitches thrown, regardless of pitch type, provides a meaningful measure of pitch variability, so I included variables for that as well. So we talked about distance before. I decided to include a weighted Mahalanobis distance measurement that weighted the distance between the pitch clusters by the frequency with which the number of pitches in those clusters. And I also included the entropy variable, which we mentioned earlier, to measure the overall variability and uncertainty caused by the number of pitch types and the frequency with which they were thrown. And finally, several other variables were included, such as a pitcher's strike rate, the number of pitch types, and an indicator variable identifying National League versus American League pitchers, because National League pitchers have the benefit of facing opposing pitchers in the lineup more frequently, and so that can improve their strikeout rates. So one quick note about strikeout rates and why this was included in the analysis. Since strikeout percentage is highly correlated with strike rate, pitchers with the same pitch characteristics may have different strikeout percentages simply because one pitcher throws more strikes than another. And since this analysis seeks to isolate the impact of changes in velocity and movement among different pitches, strikeout percentage or strike rate was included as a proxy for accuracy and to normalize differences between different pitchers. There we go. Okay. So what did we learn? A random forest model performed the best against the test set. It had a mean absolute error against the test set of 2.94 percentage points, and almost 87% of the predictions were within 5 points of their actual strikeout percentage. The table on the right lists the 10 predictions with the lowest errors against the test set, and each of these has an absolute prediction error of 0.21 percentage points or less. So what does this all mean? What did we learn? Well, the variable importance plot that we see on the left shows the variables that have the greatest influence on a pitcher's strikeout percentage. Just the top 10 variables are listed here on this chart. But maximum velocity and to no surprise, strike rate have the greatest impact on strikeout percentage. The strong influence of high velocity pitches and the ability to throw strikes is consistent with both intuition and some prior research that's been done. But somewhat surprising, however, was the importance of vertical movement relative to the other pitch characteristics that were studied. So the size of the vertical movement interquartile range, the IQR, and maximum vertical movement are more important predictors of strikeout percentage than the ability to change speeds and horizontal movement. Somewhat surprising. And moreover, there was no correlation between the number of different pitch clusters or pitch types and a pitcher's strikeout rate. What matters more was maximum velocity, strike rate, and vertical movement of the pitches. So this is my last slide, and to finish up here, there are a few conclusions that I took away from my research. In addition to identifying the pitch characteristics most likely to increase strikeouts, the insights in this analysis may be used to identify potentially high strikeout pitchers with otherwise unremarkable pitching characteristics. And within a game, this analysis may help managers determine when to remove a pitcher. As a pitcher increases his strike count, managers can monitor these variables and other variables that are likely to affect his strikeout rate. And so going forward, how can this research be brought forward for additional innovations and developments in the future? There's several questions that we could ask based on this research and that I plan to look at in the future. One, do the factors that affect strikeout percentage change based on the time through the batting order? And are these same elements indicative of relief pitcher strikeout rates versus just starting pitchers? And to what extent do batter contact rates affect this? You know, batters that are high contact, are they better able to make contact with high vertical movement pitches and therefore reduce their strikeout percentage? And finally, can pitch location, sequencing, et cetera, some of these other variables that are included in a pitcher's stuff, can they be incorporated into this research to better identify strikeout percentages? But ultimately, however, these findings can be used to identify the best situational pitchers and adjust pitching strategies based on the matchup. Thank you for your time and for the opportunity to share my research. And I can take the next couple of minutes to answer any questions.
Hi, yeah, one question here.
Yeah.
Have you run this analysis against swinging strike rate instead of strikeout rate? So I'm just kind of interested to see
are there pitches that are more for, say, call strike versus swinging strikes and so on?
Yeah, good question. Thanks. Short answer is no, I didn't. I easily could, but I had to pick one metric for determining performance, and I looked at swinging strike rate. I even looked at WAR and FIP percentage. But I have some research, and this was part of my master's thesis, so this is the 9-page version of a 48-page document. But so sparing you all the details, it turns out that the strikeout rate actually was determined to be the most accurate predictor of and consistent predictor of performance year over year, which is why I chose that over swing and strike rate. But I think that's a great point, and I think it's something that I could look at going forward.
I know you mentioned pitch tunneling and how it's definitely been a factor in affecting strikeout rates. I was just wondering if you considered adding as a variable to potentially your research, and if you think it might reduce the small amount of error that you have already in your research, because obviously perceived velocity is a lot different than actual velocity to the hitter.
Yeah, for sure. I didn't add it. The only aspect of the pitch tunneling research that I did incorporate were changes and differences in arm release point, so the release point of the baseball, but not the actual perceived velocity that can come with some of the pitch tunneling research. That was not a variable that I included. Again, I was trying to simplify the analysis, and that was kind of where I landed. I had to draw the line somewhere, but great question. Thank you.
Given the importance of vertical movement that was raised in the research, have you considered revisiting previous pitch sequence research with this in mind?
I have, yes, I have. So yes, but to give you a little more color on that answer, before I began this research, I actually wanted to do pitch sequencing research, and it was something that I spent several weeks looking at and trying to model. And I just went this way for a number of different reasons. I think that is definitely something that I want to do, and as I mentioned on the last slide, I think some of these findings can be incorporated with pitch sequencing and location research to improve the results and to reduce some of the errors, hopefully. So yeah. Okay, great. Well, thank you very much. Appreciate you coming. Enjoy the rest of your conference.